All right, this is one last little set of hints and reminders about anything for RC2, which is your blue sheets. You have this sheet on a blue sheet of paper. So this is 6.8C, 8.6A, 8.6B. I want to remind you one more time, acceleration is something you can feel when an object speeds up, slows down, or changes direction. Acceleration is caused by unbalanced forces. So if there aren't any unbalanced forces, then there's no acceleration. There can still be movement, but an object's not accelerating. Acceleration is net force divided by mass. To know acceleration, you've got to have net force and mass. Now, on your formula chart for the STAR test, you have a formula that you can use, but it's not in this arrangement. So hang on. All right, on your formula chart, you have net force is equal to mass times acceleration. Again, draw your triangle with that little T in the middle. Things that are side by side will go on the bottom. So this is mass and acceleration. Force will go on top. Force is equal, so put your thumb on force, and that's mass times acceleration. If you wanted mass, that would be force divided by acceleration. And if you wanted acceleration, that's force divided by mass. Okay? Just a reminder, up here we did something similar, except we had mass divided by volume, so we had to have m on top and v down on the bottom, and then we just put density in the other little box. Okay? But you do have a formula for acceleration, it's just not arranged for acceleration on the formula sheet. Okay? But force, mass, and acceleration, those are the things that you need to go from one to the other. Okay, just a reminder, you can also calculate acceleration by change in velocity divided by time. That's not on your formula sheet, and they usually don't ask that. They do actually give you the formula for speed, which is distance divided by time. Okay, so those are the only formulas that they give you. And of course, the other side of this sheet of paper is the periodic table. Okay, so one more time, acceleration can be change in velocity divided by time. Acceleration can be calculated also by net force divided by mass. I cannot overemphasize the importance of you knowing that these three things are related. Okay. Next, please go over your graphs one more time. Whenever you have a graph tomorrow on the STAR test, it's either going to be a distance versus time graph, or it'll be like a velocity versus time graph. If they, are trying to spice it up with a little variety, they may say position versus time, but position is like distance. What is your position? How far away are you? Okay. They might give you like a speed divided by time. Remember, speed and velocity are closely related. Velocity is just speed with a direction. So distance divided by time or velocity divided by time, but you've got to notice which one you're dealing with because that's very important. Because here on a velocity versus time graph, if you have a line that slants up, that object, the velocity value is increasing, which means it's speeding up. But down here, if it's a distance versus time graph, then the distance value is getting bigger, and that just means that the object is moving. Okay? So go over these one last time. Now, one more thing I'm going to point out before we move on from the graphs. Remember that a horizontal line means something different on a distance versus time graph. On a distance versus time graph, that means that the distance value isn't changing, so this object isn't moving. But on a velocity versus time graph, a horizontal line just means that the velocity value is not changing, which means they're moving at a constant velocity, meaning no acceleration. So please, please, please go back over your graphs one more time. All right, this is your blue sheet 8.6 ABC. Obviously mine's not blue because mine's the original with all the colors. All right, you have to know how to combine forces. It doesn't matter whether it's a pull or whether it's a push What you need to pay attention to is, are the arrows pointing in a different direction or are they pointing in the same direction? So here you have 7 to the left and 15 to the right. 15's bigger, so your net force is 8 to the right because you take the difference because they're pointing in opposite directions. Here you've got 7 to the right, like as a push, 15 to the right as kind of a pull, but they're both pointing to the right, so you add them. And the direction will be in the direction of the two individual forces because they both point the same way. Okay, here you've got 15 to the left, 7 to the right. 15's bigger, so this time it's going to move 8 to the left. Here, again, we have both of them pushing, but they're pointing in the same direction, so again, we add them. Okay, pay attention to which way the arrows are pointing. It's not as important to say, oh, it's a push, or oh, it's a pull, or whatever. Okay, so the bigger force wins as far as the direction of the net force. Arrows pointing in the same direction will add. Arrows pointing in opposite directions will subtract. All right, some of you are still struggling with kinetic and potential energy. Basically, your total mechanical energy of an object is going to be its kinetic energy and its potential energy. And usually they're going to talk about like gravitational potential energy. So let's look at the roller coaster. Up here, it's got both kinetic and potential, but the kinetic happens to be 0 unless it's already starting to roll. So it's high up, so it's got lots of potential, no kinetic because it's not moving. Well, then it rolls down the hill and it gains speed. So the kinetic energy is going up because it's getting faster and faster, but the potential energy is going down because it's heading towards the bottom of the hill. Down here, the little roller coaster cart is going its fastest, so it's basically all kinetic and no potential because the height above the ground is 0. And then it starts to make its way back up the next hill. It's going to slow down, so it's going to lose kinetic energy, but it's going to build potential because it's getting higher again. Okay, whether it's a roller coaster, whether it's a person going up and down a hill on a bicycle, whatever. The relationship is that the total energy stays the same, but as one goes up, the other one typically goes down. Let me show you a very quick simulation of what I'm talking about. Okay, look over here. All right, let's do the bar graph and put the skateboarder up there. Okay. Pause it. Okay. At the top, it's all potential because they're nice and high above the ground. As they skate down and get faster, the potential is going to go down, but the kinetic energy, the energy of their motion, is going to go up. But you notice that they just kind of trade places, but the total energy stays the same.